Right now, somewhere in northern Chile, a robotic observatory is photographing the night sky with a camera the size of a small car. And by the time it finishes its 10-year survey, it will have collected more data than every book, photograph, and document ever produced by the human species combined. And even then, it will have mapped less than 1% of the galaxies we believe exist in the observable universe. That gap between what we can measure and what actually exists is not just a problem for astronomers. It is, strangely enough, at the center of one of the strangest questions in modern science. Are we living inside a simulation? This question used to belong entirely to philosophy. Today, it sits awkwardly between physics, computer science, and metaphysics. And a surprising number of serious researchers have started taking it seriously. Not because they believe we are living in a video game, but because the question forces us to confront something deeply uncomfortable about the nature of information, computation, and reality itself. In the year 2003, a philosopher named Nick Bostrom published a short paper that has been quietly unsettling people ever since. His argument was not really about whether we live in a simulation. It was about probability, and it led to a conclusion that very few people enjoy hearing. Bostrom argued that one of three things must be true. Either civilizations like ours almost always destroy themselves before they ever develop the technology to build detailed simulations of conscious minds, or advanced civilizations exist but choose, for some reason, never to run such simulations, or we are almost certainly living inside one right now. The logic behind this is simple. And that simplicity is exactly what makes it so hard to dismiss. Start with two assumptions that most physicists and computer scientists already accept in some form. First, that consciousness does not require biological neurons specifically. If a system processes information in the right way, organized in the right pattern, there is no obvious reason it could not give rise to a mind, regardless of whether that system is built from carbon, silicon, or something else entirely. Second, assume that technological civilizations tend to keep getting better at computation over time. Not infinitely, not magically, just steadily, the way ours has for the last 100 years. If both of those assumptions hold, then somewhere down the line, a sufficiently advanced civilization would eventually be able to run simulations detailed enough to contain minds that are, from the inside, indistinguishable from biological minds. They would think, feel, remember, and be utterly convinced of their own reality, with no idea that the universe around them was being computed. Now here is the part that turns this from an interesting thought. Experiment into something with real statistical weight. Once a civilization can run even one such simulation, there is no reason to stop at one. Computing power that can simulate a single conscious mind can likely simulate millions, then billions, then trillions, especially as hardware improves and costs fall. We have already seen a small-scale preview of this in our own world. In the space of roughly 50 years, humanity has gone from building room-sized computers that could barely perform basic arithmetic to running models with parameters numbering in the hundreds of billions, training them on essentially the sum of recorded human writing. We have not simulated a conscious mind yet, as far as we know, but we have demonstrated that computational scale can increase by many orders of magnitude within a single human lifetime. So picture the long run. If it is possible, even once, for a civilization to build minds inside a computer, then, across the vast span of time available to any sufficiently old and technological civilization, the number of simulated minds would not just exceed the number of biological minds, it would dwarf it. Today, there are roughly 8 billion people alive, and estimates suggest that figure represents something like 7% of every human being who has ever lived since our species first became behaviorally modern around 200,000 years ago. That is the entire tally of biological humans across 200 millennia. Compare that to the trillions of digital agents, characters, and simulated entities that have already been created in just the last few decades of computing, most of which are far simpler than a human mind. But the trend line is unmistakable. The capacity to create digital minds, once it exists at all, scales explosively. Which brings us to the statistical punchline. If you are a conscious being wondering what kind of mind you are, and the vast majority of conscious minds in existence are simulated rather than biological, then on pure probability, you are far more likely to be one of the simulated ones, not because of anything special about you, but simply because there are so many more of them. Bostrom's trilemma, then, is really an attempt to find the escape hatch from that conclusion. The only ways to avoid it are either that civilizations never reach the technological threshold required because something stops them first. War, collapse, resource exhaustion, runaway, artificial intelligence, or any of a dozen other extinction scenarios. Or that civilizations reach that threshold but deliberately choose not to use it, perhaps for ethical reasons, perhaps because creating countless suffering minds for entertainment or research turns out to be something every sufficiently wise civilization recognizes as a bad idea. If neither of those holds, the numbers point one direction. This is why Bostrom's argument has a strange double edge to it. If we could somehow determine, with confidence, that we are not living in a simulation, that would actually be troubling news, because it would suggest that one of the first two options is true, that no civilization, anywhere, ever, manages to survive long enough or chooses freely enough to build such simulations. Given how close our own civilization already is to some of the prerequisite technologies, that would imply something is likely to go very wrong for us, possibly soon. On the other hand, if we are living in a simulation, the philosophical vertigo is obvious, but the existential threat is, in a sense, smaller. A simulated civilization that has already produced one layer of simulated minds has, by definition, already crossed the threshold that the doomsday scenarios worry about. So the question of whether we live in a simulation is not just an idle thought experiment for late-night conversations. According to Bostrom's reasoning, it is entangled with the question of how much time humanity has left, which raises the obvious follow-up. Is there any way to actually investigate this? Can we look for evidence, one way or the other? To answer that, we first need to understand just how staggering a task it would be to simulate something like our universe in the first place. Because if it turns out that simulating a universe at our level of detail is fundamentally, mathematically impossible, no matter how advanced your technology, then the entire argument collapses. So let's start there. How much information would it actually take to simulate everything? High in the Andes Mountains of northern Chile sits a barren, windswept summit called Cerro Pacho. It is a harsh place, dry, cold at night, and far from almost everything, which is exactly why, over the past decade, it has become home to one of the most ambitious instruments ever built for looking at the sky. The Vera C. Rubin Observatory. At the heart of this observatory is a digital camera, roughly the size of a small car, with a resolution of 3,200 megapixels. For comparison, a high-end smartphone camera might capture an image at around 50 megapixels. This camera captures an image with more than 60 times that resolution in a single exposure, every few seconds, all night, every clear night, for years. Each night, the observatory generates roughly 20 terabytes of raw data. To put that in perspective, 20 terabytes is enough storage to hold several million high-resolution photographs, or tens of thousands of hours of video, and the observatory produces that volume of data every single night. Over its planned 10-year survey, the total accumulated dataset is expected to reach around 500 petabytes. 1 petabyte is roughly 1 million gigabytes. 500 petabytes has been compared, by some estimates, to the equivalent of every word ever written by every human being throughout history, captured many times over, just in images of the sky. With that fire hose of data, the observatory aims to catalog roughly 17 billion stars within our own galaxy, the Milky Way, and around 20 billion galaxies across the nearby universe. It will photograph the same patches of sky over and over, creating what is essentially a time-lapse movie of the cosmos, capturing exploding stars, asteroids, comets, and the faint signatures of dark matter bending light as it passes massive objects. And yet, for all of that, here is the part that should stop you in your tracks. Even with 17 billion catalogued stars, the Vera Rubin Observatory will capture less than 5% of all the stars believed to exist in the Milky Way alone. And its catalog of 20 billion galaxies, the largest ever assembled by humanity, will represent less than 1% of all the galaxies estimated to exist within the observable universe. For every exploding star, every supernova that the observatory detects, astronomers expect that thousands more will go entirely unnoticed, too far away to faint, or simply not pointed at during the brief window when they are visible. This is not a flaw specific to this one telescope. It is the pattern of the entire history of astronomy. Every instrument we have ever built, from Galileo's first telescope to the James Webb Space Telescope, has only ever sampled a tiny fraction of what is actually out there. The observable universe, the portion of the cosmos from which light has had time to reach us since the beginning, spans roughly 93 billion light-years across. Within that volume, current estimates suggest there are around 10 to the power of 88 individual particles, a number so large that writing it out in full would require 89 digits. So here is the obvious question for anyone thinking about simulation. If a civilization wanted to build a perfect one-to-one simulation of a universe like ours, how much information would that actually require? In 2009, two physicists, Charles Egan and Charles Lineweaver, attempted to estimate exactly that. Their calculations suggested that the total information content of the observable universe, the number of bits required to fully describe its state, comes out to roughly 10 to the power of 122 bits. To make sense of a number like that, it helps to look at smaller examples from their analysis. A single star, they estimated, contains roughly 10 to the power of 59 bits of information, accounting for the state of every particle within it. A single gram of water contains roughly 10 to the power of 24 bits. For comparison, one rough estimate of the total combined storage capacity of every computer, server, and hard drive on planet Earth comes out to somewhere around 200 zettabytes, which is also in the neighborhood of 10 to the power of 24 bits. In other words, all of human civilization's digital storage, every data center, every phone, every laptop, every archive, holds roughly the same amount of information as a single gram of water. If you tried to describe that water down to the state of every particle within it, and the universe as a whole holds roughly 10 to the power of 122 bits. The gap between what we can store and what would be required to fully describe even the observable universe is almost impossible to put into ordinary language. It is not just large. It is large in a way that breaks our usual intuitions about big numbers entirely. And remember, this is only the observable universe, the portion within causal reach since the beginning of time, roughly 13.8 billion years ago. Beyond that boundary, there could be more universe, perhaps unimaginably more, that we will never be able to detect, measure, or interact with, simply because light from those regions has not had time to reach us and never will, given the accelerating expansion of space itself. So, if you were a civilization trying to build a simulation that captured every particle, every quantum state, every interaction, down to the level described by that 10 to the power of 122-bit figure, you would need a computer with a memory capacity larger than the system it is simulating. That seems like an obvious dead end. But here is where the conversation gets more interesting, because nobody who has seriously proposed that we live in a simulation has suggested that it would need to be a perfect, particle-by-particle replica of everything, all at once, all the time. Real simulations, the kind we already build today, don't work that way. They cut corners constantly, intelligently, and almost invisibly. And looking at how our own simulations cut those corners turns out to be remarkably revealing. Let's start at the largest scale humans currently simulate, the universe itself, or at least large chunks of it. One of the most widely used tools for this is a piece of software called a repo, first released in 2009 and still actively developed and updated today. A repo works by taking a region of space, sometimes a few 100 million light years across, sometimes a few billion, and dividing it into an enormous number of individual cells, somewhat like a three-dimensional grid, except the grid is not fixed. It can stretch, shrink, and rearrange itself depending on what is happening in each region. Each cell tracks a set of properties: how much dark matter is present, how much ordinary gas, the temperature and pressure of that gas, the strength of any magnetic fields, and the state of radiation passing through. From this information, the simulation can estimate how many stars are likely forming within that cell, whether any supernova are occurring, and whether a supermassive black hole nearby might be blasting out jets of energy and matter, given a snapshot of the universe at one point in time. The software then applies the laws of physics. gravity, fluid dynamics, thermodynamics, and steps forward, calculating what the universe looks like millions of years later. Dark matter clumps together under gravity. Gas cools and collapses into the seeds of new stars. Galaxies drift toward each other and eventually merge. The simulation automatically adds finer detail in regions where complex things are happening, like the dense core of a forming galaxy, while keeping things coarse and simple in the vast, mostly empty stretches of space between galaxies, where almost nothing is changing. This adaptive approach is the first major clue about how a simulation, any simulation, can represent something enormously complex without literally tracking every particle. It allocates computational effort where it matters and skips the detail where it doesn't. The emptiness between galaxies doesn't need particle-by-particle tracking, because at human observational scales, nothing meaningful is happening there that requires that level of resolution. But here's the catch. Even the most powerful cosmological simulations, running on some of the largest supercomputers on the planet, cannot simultaneously model the large-scale structure of the universe and the fine detail of, say, a single planet's atmosphere, or the chemistry happening inside a living cell. The resolution required for galaxy formation is measured in thousands of light-years per cell. The resolution required to understand a hurricane is measured in kilometers. The resolution required to understand a chemical reaction is measured in the size of individual molecules. These are different problems, requiring entirely different simulations, run separately because no current computer can do both at once. So let's drop down a scale. On the 13th of August, 1958, a team at the University of Chicago ran what is often considered the first computerized weather forecast for a real storm. At the time, a tropical system named Becky was moving across the Atlantic toward the Americas. The researchers fed in digitized measurements of the storm's wind speeds and pressure readings, applied physical equations describing how air masses move and interact, and produced the first computer-generated prediction of where the storm would go next. Decades ago was the ancestor of the global weather forecasting systems we rely on today. Modern meteorological agencies operate networks of satellites that continuously stream data, wind speed, humidity, temperature, pressure, down to ground stations, which feed into massive simulations running around the clock on dedicated supercomputers. These models are now good enough that when a major hurricane forms, forecasters can predict its likely path several days in advance with meaningful accuracy, something that would have seemed like science fiction in 1958. But even these enormously powerful weather models have a resolution limit, typically somewhere around 1 to 2 kilometers. Below that scale, the simulation can no longer track individual features. It cannot follow a specific raindrop, let alone the water molecules inside that raindrop. To model that level of detail, you need an entirely different kind of simulation, one that operates at the scale of individual particles and molecular interactions, which brings us to a strange detour through the world of video game consoles. On the 23rd of September, 1992, at the Nevada test site in the United States, the ground shook as the last underground nuclear test conducted by the United States took place. It was the 154th nuclear test carried out at that site. and it would be the final one before the United States signed the Comprehensive Nuclear Test Ban Treaty in 1996. After that point, the United States, like other nuclear-armed nations that observed similar treaties, faced a peculiar problem. Nuclear weapons in storage degrade over time. Materials change, components age, and without the ability to physically test a live weapon, how do you verify that an aging warhead would still function as designed if it were ever needed, or, just as importantly, that it would remain safe in storage? The answer was simulation. The United States Department of Energy became one of the largest funders of supercomputing in the world, specifically to model the physics of aging nuclear weapons in extraordinary detail, simulating the behavior of materials under conditions that could no longer be tested directly. This appetite for raw computational power led to an unusual moment in 2010, when the United States Air Force Research Laboratory needed a new supercomputer and discovered an unlikely source of cheap, powerful processors, the Sony PlayStation 3. Sony had partnered with IBM to design a powerful chip for the console called the Cell Processor, and it turned out that the kind of math this chip was built to do, the math behind realistic game graphics, was strikingly similar to the math needed for processing high-resolution satellite imagery. So the Air Force connected together 1,760 PlayStation 3 consoles into a single cluster, nicknamed the Condor Cluster, and used it to process satellite data at roughly 1/10 the cost of a conventional supercomputer built from scratch. So across these examples, from galaxy formation to hurricanes to nuclear weapons aging to satellite image processing, a clear pattern emerges. Every simulation we build, it picks the level of detail that matters for the question being asked, and discards or averages out everything below that threshold. A galaxy simulation doesn't need to know about individual atoms. A weather model doesn't need to know about individual raindrops. And so the question becomes, if our universe is itself a simulation, what is its threshold? Where does the detail stop, and what gets approximated? To answer that, we have to go to the smallest scale physics can currently describe, and ask whether the universe itself shows any signs of cutting corners. If you wanted to find evidence that the universe is a simulation, where would you even look? Ancient texts and religious traditions are full of creation stories, but those are not the kind of evidence a physicist can work with. Instead, some researchers have suggested looking at the fundamental constraints of physics itself, the rules that never seem to bend, no matter what we throw at them, and asking whether those rules look more like laws of nature, or more like the engineering compromises a programmer would have to make. Consider the speed of light. Light travels at roughly 9,792,458 meters per second, and nothing in the universe, as far as we know, can exceed that speed. We usually describe this as a fundamental law baked into the geometry of space-time itself. But there is another way to describe it. In any computational system, information cannot move between parts of the system faster than the system's processing speed allows. If you think of the universe as being divided into regions, the speed of light looks suspiciously like a kind of universal refresh rate, the maximum speed at which a change in one region of space can be communicated to another. If the universe were a simulation, and that simulation needed to remain internally consistent, you would expect exactly this kind of speed limit. A hard cap on how fast information propagates, so that no region ever gets ahead of what the rest of the system has computed yet. Then there is the fine-tuning problem, which has puzzled physicists for decades, regardless of whether you bring simulations into it at all. The fundamental constants of physics, the strength of gravity, the mass of the electron, the strength of the force that holds atomic nuclei together, all sit within an extraordinarily narrow range that allows stars, chemistry, and ultimately life to exist. Nudge several of these constants by even a small percentage in either direction, and you get a universe with no stars, no complex chemistry, nothing resembling what we see around us. To someone inclined toward religious explanations, this has often been read as evidence of a creator who set the dials just right. To someone thinking in terms of computation, it looks like something else. Parameter tuning. If you were running an enormous number of simulated universes, each with slightly different physical constants, most of them would be sterile, lifeless, computationally uninteresting. But a small fraction, by chance, would land in the narrow range that produces stars, chemistry, and eventually observers. Those are the only ones anyone would ever be around to look at and ask, why is this universe so perfectly tuned? It is a selection effect rather than a coincidence requiring explanation. In the same way that a person who wins the lottery shouldn't be shocked that they specifically won, given that someone necessarily would. And then there is the smallest scale of all. As physicists zoom into the structure of space-time itself, down to a scale known as the Planck length, roughly 10 to the power of -35 meters, the smooth, continuous picture of space and time that general relativity describes begins to break down. Some approaches to quantum gravity, including a framework called loop quantum gravity, suggest that space-time itself might not be perfectly continuous at all, but instead made up of discrete, indivisible units, somewhat like how a digital photograph, despite looking smooth from a distance, dissolves into individual pixels when you zoom in far enough. If that turns out to be correct, it would mean the universe has a minimum resolution, a smallest possible unit of length and time below which the concept of smaller simply stops making sense, which, again, is exactly the kind of property you would expect from a system with finite computational resources. You cannot render detail smaller than your smallest unit of storage. None of this proves anything, of course. The speed of light, fine-tuning, and the Planck scale all have explanations within standard physics that don't require invoking a simulation at all. But what is interesting is that these explanations and the simulation framing are not mutually exclusive. A universe built on quantized finite information would naturally produce exactly these features. A speed limit on information transfer, an apparent fine-tuning visible only to observers who happen to exist within the narrow range that permits them, and a smallest unit of space and time. There is one more clue, and it might be the strangest one of all, because it comes not from cosmology, but from the behavior of individual particles. Quantum mechanics has a famously bizarre feature. At the smallest scales, particles don't seem to have definite properties until they are measured. An electron can exist in a haze of probabilities, a superposition of multiple possible locations or states, right up until the moment something interacts with it, an observation, a measurement, at which point it snaps into a single, definite outcome from a physics standpoint. This is one of the most studied and best confirmed phenomena in all of science, verified across thousands of experiments. But from a computational standpoint, it looks remarkably like an optimization technique. Imagine designing a simulation of an enormous universe, full of trillions of particles, but knowing that most of those particles, at any given moment, are not being directly observed by anyone or anything capable of recording the result. Rather than continuously calculating the precise state of every single particle everywhere, all the time, an efficient system might instead only finalize the state of a particle at the moment it is actually measured or interacted with in a way that matters, leaving everything else as a cloud of possibilities, a placeholder, until it becomes necessary to render the detail. This is, of course, an analogy, and analogies between physics and computer science need to be treated carefully. But it is a striking one because it would mean that the strangest, most counterintuitive feature of quantum mechanics, the fact that reality seems to wait until you look at it before deciding what it is, might be exactly the kind of behavior you'd expect from a system economizing on computational resources. And this brings us to what might be the single largest practical obstacle facing anyone or anything that wanted to build a complete simulation of a universe like ours. Quantum mechanics itself is brutally difficult to simulate using the kind of computer you are probably reading or listening to this on right now. Every computer you have ever used, your phone, your laptop, the servers that run the internet, operates on the same basic principle. Information is stored as long strings of binary digits, ones and zeros, which correspond physically to transistors being either switched on or switched off, either carrying an electrical charge or not. This binary system has proven extraordinarily powerful. It can simulate the formation of galaxies, predict the weather, model the aging of nuclear materials, and generate increasingly convincing artificial intelligence. But binary logic runs into a wall the moment you try to use it to simulate quantum mechanics. In the quantum world, particles don't simply have a value of 1 or 0. They can exist in superpositions, simultaneously holding multiple possible values, with definite outcomes only emerging upon measurement. Worse, particles can become entangled, meaning the state of one particle becomes linked to the state of another, no matter how far apart they are, such that measuring one instantly tells you something about the other. To simulate this behavior on a classical binary computer, you essentially have to brute force it, tracking every possible combination of every possible state for every particle involved. And the number of combinations grows exponentially with each additional particle. Add a second particle, and the number of combinations roughly doubles. Add a third, and it doubles again. By the time you're trying to simulate even a few dozen interacting quantum particles, the number of combinations exceeds anything a classical computer, even the largest supercomputers on Earth, could ever hope to track. The memory and processing requirements explode past anything physically realizable, long before you get anywhere close to the complexity of, say, a single atom's worth of electrons. let alone the trillions upon trillions of particles in a star or a brain. This problem was understood clearly by physicists decades ago. In a now famous lecture at the close of 1981, the physicist Richard Feynman put it bluntly: nature isn't classical, and if you want to simulate nature, your simulation needs to be quantum mechanical too. At the time, this was more of a provocative observation than a practical proposal. Nobody knew how to actually build a quantum computer, or even what that would mean in practice. Among those wrestling with this idea was John Wheeler, a physicist whose influence on 20th century physics is hard to overstate. Despite the fact that his name is far less widely known than many of the people he trained or worked alongside, Wheeler had been a postdoctoral researcher under Niels Bohr, one of the founders of quantum mechanics, and went on to mentor dozens of graduate students and postdoctoral researchers who would go on to shape the field for decades. In the early 1980s, at a gathering hosted by Wheeler specifically to encourage freewheeling conversation about the foundations of physics and computing, a young researcher named David Deutsch was in attendance. Deutsch had been thinking about Feynman's challenge, and unlike most people who heard it and filed it away as an interesting but impractical idea, Deutsch set out to actually solve it. A few years later, Deutsch published the foundational papers that essentially invented the field of quantum computing. His insight was that instead of trying to force quantum systems into binary logic, you could build a computer whose fundamental units of information, instead of being restricted to a value of either 0 or 1, could exist in superpositions of both simultaneously, mirroring the very quantum behavior the computer was meant to simulate. These units became known as qubits, short for quantum bits. While an ordinary bit is like a coin lying flat on a table, showing either heads or tails, a qubit is more like a coin spinning in the air, in some sense representing both heads and tails at once, with the specific outcome only becoming fixed at the moment you catch it and look. The practical upshot is enormous. A classical computer working through a complex problem generally has to check possibilities one at a time, or in limited parallel batches. A quantum computer, because its qubits can represent multiple states simultaneously, can, in certain types of problems, explore a vast number of possibilities at once, with the wrong answers effectively canceling each other out through quantum interference, leaving the correct answer as the dominant outcome when the system is finally measured. To get an intuitive feel for this, imagine you have a mouse problem in your house. The classical approach is to get a cat and let it wander from room to room until it finds the mouse, or, if you're impatient, buy a separate cat for every room, which works but is wasteful and expensive. The quantum approach would be like having a single cat that exists in a kind of superposition across every room simultaneously, searching everywhere at once. And when you finally check in the morning, you find one cat in one room having already caught the mouse, without ever needing a small army of identical cats. Quantum computers built using this principle are real, and they exist today, though they remain limited in scale. The most powerful, publicly known quantum computer, IBM's Condor processor, contains 1,121 qubits, a number that sounds tiny compared to the billions of transistors in an ordinary smartphone chip. But because of the way qubits scale, a relatively small number of them can, for certain specific problems, vastly outperform classical computers with far more raw components. The hardware required to keep these qubits stable is enormous and elaborate, often involving intricate arrangements of cooling systems that keep the processor at temperatures colder than deep space, because even tiny amounts of heat or vibration can disrupt the delicate quantum states the computer relies on. It's important to be clear, though, that quantum computers are not simply faster versions of regular computers. For the vast majority of everyday computing tasks, browsing the web, writing documents, running spreadsheets, a quantum computer offers no advantage at all and might even be worse. Their power is narrow, but, in certain cases, transformative. And one of those cases happens to be the most relevant one for our purposes: simulating quantum systems themselves. As Deutsch worked through the implications of quantum computing, he arrived at a conclusion that went far beyond engineering. He became, and remains, one of the most prominent defenders of what's called the many worlds interpretation of quantum mechanics. The idea that every time a quantum event has multiple possible outcomes, all of those outcomes actually happen, each in its own separate, branching version of reality. In this view, the universe is constantly splitting into a staggering number of parallel versions, one for every possible quantum outcome, with each branch completely unaware of the others. For Deutsch, this isn't just a philosophical curiosity bolted onto quantum mechanics. He has argued it is the explanation, the only interpretation that takes the mathematics of quantum theory completely at face value, without requiring extra rules to be bolted on afterward. And under this interpretation, quantum computers make a strange kind of sense. Their power comes precisely from harnessing computations happening across these parallel branches simultaneously, with the branches interfering with each other in ways that amplify correct answers and cancel out incorrect ones. Not everyone in physics accepts the many worlds interpretation, and there remains no consensus on which interpretation of quantum mechanics is correct. A debate that has continued for almost a century without resolution. But regardless of which interpretation you favor, nobody disputes the practical computational power that quantum systems demonstrably have. And this is where things circle back to the question of simulation. Deutsch himself has pointed out that the most important future application of quantum computers may not be cryptography or optimization problems or any of the other applications that get discussed in the news. It may simply be using quantum computers to simulate quantum systems, because, as he put it, that is the one application where we know for certain that classical computers fundamentally cannot keep up. No matter how much we improve them, think about what this means for the question of a universe-sized simulation. Every process in our universe that depends on quantum mechanics, and there are more of these than most people realize, would require a quantum computer to simulate efficiently. When a star fuses hydrogen into helium in its core, the rate at which that fusion happens is governed by quantum tunneling, a process where particles have a small probability of passing through energy barriers that, classically, they shouldn't be able to cross at all. When sunlight strikes a leaf and is absorbed by chlorophyll molecules, the efficiency of that energy transfer depends on quantum effects within the molecule, even the chemistry happening in neurons. As you think through this sentence, involves quantum mechanical processes at some level, So any civilization attempting to build a complete simulation of a universe like ours would, almost certainly, need a quantum computer as one of its core components, not as an optional add-on, but as a fundamental requirement. Because so much of what happens in our universe, from stellar fusion to photosynthesis to the chemistry of cognition, is quantum mechanical at its core. But even granting access to a sufficiently powerful quantum computer, there's a further obstacle, one that has nothing to do with raw computing power at all. It's a problem known as emergence, and it might be the deepest one of all. Here's the issue. Just because you have a set of fundamental physical laws that accurately describe how things behave at one scale, doesn't mean those laws, even run perfectly and with unlimited computing power, automatically tell you how things behave at a different, larger scale. We have an extraordinarily successful theory called quantum field theory, which describes how fundamental particles and forces interact with remarkable precision. Precision that has been tested in particle accelerators to many decimal places. But quantum field theory on its own doesn't tell you how a protein folds into its three-dimensional shape. It doesn't tell you how neurons in a brain communicate to produce a thought. It doesn't tell you how billions of stars organize themselves into the spiral arms of a galaxy. These phenomena emerge from the underlying quantum interactions, in the sense that they are, in principle, the result of those interactions playing out at scale. But the patterns themselves require entirely different theories, biology, chemistry, fluid dynamics, to describe and predict. This is sometimes described by saying that more is different. A system made of an enormous number of simple, well-understood components can display behaviors that are not simple, not obvious from the rules governing the individual components, and in practice, not derivable from those rules without enormous additional theoretical work. Work that in many cases hasn't been done yet, because the relevant fields, protein folding, neuroscience, and others, are still active areas of ongoing research, with major open questions. So even a hypothetical simulation with unlimited quantum computing power, capable of perfectly modeling every fundamental particle interaction, would still face the challenge of emergence, ensuring that the right large-scale patterns, proteins, cells, brains, galaxies, actually arise from those fundamental interactions in a way that matches what we observe, rather than producing some other, equally valid but completely different outcome. It's the difference between knowing the rules of chess perfectly and being able to predict, from those rules alone, who will win a particular grandmaster level game. The rules are necessary, but nowhere near sufficient. And there's one emergent phenomenon in particular that towers over all the others in terms of difficulty, strangeness, and personal relevance to anyone asking these questions in the first place. Us, conscious, thinking, curious beings, wondering about the nature of the universe we find ourselves in. Any simulation detailed enough to be interesting, in the Bostrom sense, has to be able to produce minds like ours. Minds capable of asking exactly the question we're asking right now. In 2017, a team of researchers at Google's DeepMind division published a paper with a deceptively simple title, "Attention is all you need." At the time, it didn't make headlines outside of specialist circles. Today, it's widely regarded as one of the pivotal papers in the history of artificial intelligence, because the architecture it described became the foundation for the large language models that have since transformed how computers process and generate human language. The core idea was, in some sense, elegant. Rather than processing text strictly in order, word by word, the architecture allowed a neural network, a system of interconnected nodes loosely inspired by neurons, to weigh the relevance of every word in a passage against every other word simultaneously, capturing relationships and context across an entire piece of text at once. This mechanism, called attention, turned out to scale remarkably well. Make the network bigger, train it on more text, and its ability to generate coherent, contextually appropriate language kept improving in ways that surprised even many of the researchers working on it. This led, within a few years, to systems capable of holding fluent conversations, writing essays, answering questions, and performing tasks that only a decade earlier would have been confidently described as decades away. Some researchers and commentators began to suggest that this represented meaningful progress toward artificial general intelligence, systems with the broad, flexible cognitive abilities of a human mind, rather than narrow systems built for one specific task. Others pushed back firmly, pointing out that however fluent these systems appear, there's good reason to think they don't process or represent information the way biological brains do, and that fluency in language is not the same thing as understanding, reasoning, or consciousness. Whatever those terms ultimately mean, that debate remains very much unresolved, and it's worth being honest that nobody, not the researchers building these systems, not neuroscientists, not philosophers, actually has a settled, agreed-upon definition of consciousness, let alone a reliable test for detecting it in a system that isn't a human being. But suppose, for the sake of argument, that minds like ours really could, in principle, run on something other than biological neurons, on some future descendant of the kind of architecture behind attention is all you need, or on something we haven't invented yet. What would that mean for the simulation question, and for something that matters to almost everyone personally, free will, in a purely classical, deterministic universe, the kind of universe that 19th century physics imagined, where every particle's future position and momentum is, in principle, fully determined by its current state and the laws of physics. There's already a long-running philosophical worry that human decisions might just be the inevitable output of prior physical states, atoms bumping into atoms in predetermined ways, with the feeling of choice being just that, a feeling, layered on top of a process that was never really open-ended at all. If our universe is a simulation, you might think this worry gets worse. If our thoughts are, in some sense, code running on someone else's hardware, doesn't that make free will even more obviously an illusion? Just a feature programmed in to make the experience feel more meaningful or productive for whoever or whatever is observing it. Here's where it gets more interesting, though. Most simulations that humans build, particularly anything involving complex systems that need to behave unpredictably, things like games, financial models, or scientific simulations exploring a range of possible outcomes, rely on random number generation without genuine randomness. A complex enough system tends to either settle into repetitive, predictable loops, or produce outcomes that are technically unpredictable to the people running it, but are, underneath, fully determined by the starting conditions, meaning that, in principle, given the same starting state, you'd get exactly the same result every time. Our universe, as it happens, contains a source of randomness that appears to be genuinely, fundamentally unpredictable. Not just unpredictable due to our lack of information, but unpredictable in principle, according to our best current understanding of physics. This is the randomness inherent in quantum mechanics itself, sometimes referred to poetically as quantum foam, the sea of fluctuating quantum fields underlying everything, where the outcomes of individual quantum events are, as far as we can tell, not determined by any hidden variables, just genuinely probabilistic. If a hypothetical universe-sized simulation used true quantum randomness, generated by genuinely indeterminate quantum processes as its source of unpredictability, rather than the kind of pseudo-random number generators that ordinary computers use, which are technically deterministic sequences that merely look random, then the future of such a simulation would not be predetermined, even by someone with complete access to its starting conditions and its rules. The outcomes would be genuinely open in that scenario, even if you're a simulated mind running on someone else's hardware. Your future, and by extension your choices, wouldn't be a fixed, predetermined script that simply hasn't been revealed to you yet. It would be genuinely undetermined, shaped by processes that even the architects of the simulation couldn't predict in advance. Whether that counts as free will in the philosophically meaningful sense people usually mean is its own enormous debate, one that long predates any discussion of simulations. But it does mean that being simulated doesn't automatically collapse into being scripted. A simulation can, in principle, contain genuine openness, genuine surprises for everyone involved, including whoever built it. So where does this leave us? We've established that quantum mechanics is both the largest obstacle to building a complete simulation, requiring quantum computers that we're only just beginning to build, and potentially the very source of openness and unpredictability that would make a simulated existence not feel like a scripted one. To go further, we need to step back from computing entirely and ask an older, stranger question. How would you even know from the inside whether what you're experiencing is real? This question is far older than computers, far older than physics as we know it. Philosophers across very different traditions, from ancient Greece to classical India and its exploration of the nature of perceived reality, to Taoist philosophy in China with its meditations on dreams and waking, have circled around versions of the same puzzle for thousands of years. How do you distinguish genuine reality from a sufficiently convincing illusion? One of the most famous Western explorations of this idea comes from the 17th century philosopher René Descartes. In 1619, Descartes set himself an extraordinary task. He decided to doubt everything he believed, deliberately, systematically, to see what, if anything, could survive that doubt and serve as a foundation he could trust completely. He started with the senses. He pointed out that dreams can feel completely real while you're having them, indistinguishable from waking experience in the moment. If your senses can be fooled that thoroughly while dreaming, how can you trust them while awake? Maybe you're dreaming right now and simply don't know it. then he pushed further, into a thought experiment that has become famous in its own right. Suppose, he said, there exists an immensely powerful and clever deceiver, something capable of feeding you a constant stream of false sensations, sights, sounds, the feeling of solid ground beneath your feet, memories of a past that never happened, all of it manufactured, all of it designed to be indistinguishable from genuine experience. Descartes realized something unsettling. There would be no way, even in principle, to disprove this. Any evidence you might gather to prove the deceiver doesn't exist could itself simply be more deception, fed to you by the very deceiver you're trying to disprove. The trap appeared to be completely airtight, with no possible exit, except for one thing. Even if every sensation, every memory, every belief about the external world could be false, there was still something doing the doubting, something experiencing the uncertainty, asking the question, engaging in the process of thought itself. The deceiver could fabricate an entire world of false experiences, but it couldn't fabricate the fact that something was there, experiencing those experiences, doubting them. From this, Descartes arrived at his famous conclusion: I think, therefore I am. Whatever else might be illusion, the fact of thinking, of being a thing that thinks and doubts, seemed to be the one thing that couldn't be faked away. About 300 years later, in the 20th century, the philosopher Hilary Putnam updated this thought experiment with more modern hardware. Instead of an all-powerful deceiver, imagine your brain has been removed from your body and placed in a vat of nutrients, kept alive, with every nerve ending connected to a sufficiently advanced computer. That computer feeds your brain a perfect, continuous stream of signals, every sight, sound, touch, and sensation you would have experienced if your body were intact and walking through the world from the inside. There would be no difference. Every memory, every conversation, every mundane Tuesday morning would feel exactly as real as it does now, because, as far as your brain is concerned, that stream of signals is reality. There would be no seam, no glitch, nothing to notice, because the very faculties you'd use to investigate the question, your senses, your reasoning, even your sense that something feels off, would themselves just be more signals coming from the same source. The brain in the vat has no way to step outside itself and check. Now here's where a researcher took this from pure philosophy into something testable, at least indirectly. Donald Hoffman, a cognitive scientist, approached this puzzle not through philosophical argument, but through evolutionary modeling. He built computer simulations of populations of organisms competing to survive, where some organisms perceived their environment accurately, registering the true underlying state of the world, while others perceived only simplified signals that were useful for survival. Regardless of how accurately those signals reflected reality, the result, across many runs of these simulations, was consistent and, to many people, deeply counterintuitive. Organisms that perceived the world accurately were consistently outcompeted by organisms that perceived only useful, simplified signals. In evolutionary terms, accuracy didn't pay off. Usefulness did. Hoffman's interpretation is that natural selection doesn't favor organisms that perceive reality as it truly is. It favors organisms that perceive whatever helps them survive and reproduce, even if that perception bears little resemblance to the underlying physical truth applied to us. This suggests something genuinely strange about everyday experience. The redness and roundness of an apple, the solidity of a table, the warmth of sunlight. None of these properties exist in those forms at the level of fundamental physics. At that level, there's no redness, no solidity in the everyday sense. Just configurations of quantum fields, mostly empty space, governed by probabilistic rules. The apple looks red and round and solid because that simplified representation is fast, useful, and lets you do something practical, like eat it or avoid it, without your brain needing to process the staggering underlying complexity of what's actually there. Hoffman describes what we perceive as something like an interface, comparable to the desktop icons on a computer screen. The icon for a document isn't made of the same stuff as the file it represents, isn't shaped like it, doesn't behave like it. It's a simplified, useful stand-in, designed to let you interact with something complicated without needing to understand its underlying structure. In Hoffman's view, our entire perceptual experience, the world as it appears to us, color, shape, solidity, space, time, might be exactly this kind of interface, useful, evolved, but not a direct window onto whatever is actually, fundamentally there. This is a more modest claim than Descartes' all-powerful deceiver. Hoffman isn't arguing that the external world doesn't exist, or that it's fake in some dramatic sense. He's arguing that whatever it actually is, we've never directly perceived it, and quite possibly never could. Because our perceptual systems were shaped by evolution to be useful, not accurate, and if our perception is already, in some sense, a kind of simulation running in our own heads, an interface standing between us and whatever reality actually is, then the idea that this interface could be generated by something other than biological evolution and a biological brain, by a sufficiently advanced external system, instead stops sounding like such an enormous leap. It becomes a difference of degree of what's generating the interface, rather than a difference in kind. This is, in essence, the idea that 1999's blockbuster film, The Matrix, dramatized for a global audience, probably introducing more people to this entire line of thinking than any philosophy lecture ever had. But the film, for all its cultural impact, gets one thing quietly, interestingly, wrong. And noticing what it gets wrong takes us right back to Bostrom's argument and pushes it even further in The Matrix. The central character is unplugged from a simulated world and wakes up in what the film presents as the real, physical world, a grim, machine-dominated reality outside the simulation. The moment is framed as an awakening, a return to base reality, the genuine, unmediated truth beneath the illusion. But here's the problem with that framing, and it's a problem that follows directly from everything Putnam and Hoffman point out. If a simulation can be detailed and convincing enough to completely fool a human brain, detailed enough that nothing about the experience feels different from ordinary reality, then what would it feel like to wake up from that simulation into another one layer up, that was equally detailed and equally convincing? The answer is, it would feel exactly the same. It would feel like waking up. There's no test you could run, no sensation you could have, that would distinguish waking up into the true base reality from waking up into yet another simulation. One level removed. This is the same airtight trap Descartes identified centuries earlier, just with newer language. If the deception can be perfect, then there's no internal evidence, none whatsoever, that could ever distinguish a perfect simulation from the real thing, or distinguish one level of simulation from another, or from the actual bottom layer of reality. If such a bottom layer even exists, this is where Bostrom's argument stops being an abstract statement about probability in general, and becomes something more specific, almost archaeological. Bostrom didn't just argue that we might be in some simulation or other, run for some arbitrary purpose. He argued that if simulations of conscious beings are possible at all, the simulations that get run most often, by a wide margin, would be a particular kind, simulations of a civilization's own past. The reasoning goes like this. Imagine an advanced civilization with access to enormous computational resources, capable of running detailed simulations of conscious minds. What would they be most interested in simulating? Random, arbitrary universes with no connection to their own history seem like one option, but a far more compelling one, scientifically, historically, and even emotionally, would be simulations of their own origins, the civilizations that came before them, the historical events that shaped who they became, the individual people, choices, wars, discoveries, and accidents that, in aggregate, produced the civilization running the simulation in the first place. These would be, in a very real sense, the most interesting simulations to run, the ones that answer the question every sufficiently advanced civilization would eventually ask, how did we get here? And Bostrom suggested that such a civilization wouldn't run this kind of simulation just once. They'd likely run it many times, with variations, exploring different historical branches, different outcomes, the way historians today might use different models to explore what-if scenarios about historical events, except with the ability to actually populate those models with conscious minds, experiencing the events from the inside. If that's true, then the overwhelming majority of conscious minds that have ever existed, if simulated minds vastly outnumber biological ones, as the earlier argument suggested, would not just be simulated minds in general. They would specifically be simulated ancestors, reconstructions of a civilization's own history, run again and again by descendants curious about their own origins. Under this version of the argument, we wouldn't just possibly be living in a simulation. We would specifically be living in something more like a historical reconstruction, an experiment in understanding how a civilization came to exist, run from the inside by people who, from their own perspective, have no idea they're part of it. And there's a further twist that makes the picture even stranger. Suppose a civilization does build a computer powerful enough to simulate a universe as complex as their own, populated with conscious minds. Those simulated minds, if they're complex enough to be conscious in the first place, would presumably also be curious. They would presumably also, eventually, develop computing technology of their own. And if it's possible for one civilization to build such a simulation, there's no obvious reason why a simulated civilization, with simulated computers, running simulated physics, couldn't do the same thing, building their own simulation. Nested one level deeper, this idea of nested simulations, simulations within simulations within simulations, leads to a genuinely vertiginous conclusion. If even one civilization, anywhere, at any point, manages to start this chain, then the number of nested layers could grow enormous, limited only by however many times a civilization is willing and able to repeat the process. The real, original, base reality civilization, the one made of biological matter running on whatever the true, fundamental laws of physics actually are, would be just one layer, at the very top of what could be an enormous stack, with an enormous number of nested, simulated civilizations beneath it, each one simulating its own nested layer in turn. If that's the structure of things, then the statistical argument becomes almost overwhelming. Out of all the layers in such a stack, the odds that any particular conscious mind, picked at random, happens to be in the topmost layer, the genuine base reality, become vanishingly small. Far more likely, on pure numbers, is that any given mind is somewhere deep within the stack. A simulation running inside a simulation running inside a simulation, with the original biological base layer reality so far removed as to be functionally inaccessible, and possibly even unaware of how many layers separate it from whatever, if anything, started the whole process. It's worth pausing here, because this is the point where a lot of people understandably start to feel a kind of existential vertigo, and where some commentators take the conversation in an unnecessarily bleak direction. But there's another way to look at it. If a simulation is detailed enough to produce something that genuinely feels, in every measurable and experiential sense, exactly like consciousness, like love, like grief, like the feeling of a sunset, then in what meaningful sense is that experience less real than an experience occurring in some hypothetical, unreachable base layer that nobody in the stack could ever access or verify anyway? A sufficiently perfect simulation of a thing isn't necessarily a lesser version of that thing. In a sense, it simply is that thing, as far as anyone inside it, or arguably anyone at all, could ever tell. Which brings us back, full circle, to the question we keep returning to. What is reality, fundamentally, if every layer, simulated or not, every interface, every perception, every measurement, ultimately comes down to information, bits, being processed according to some set of rules? This question consumed the later career of one particular physicist more than almost anyone else, and his answer, however strange it sounds, turns out to have real experimental support. 1944. A postcard arrives from the front lines of Europe, where Allied forces are pushing into Germany in the final stages of the Second World War. It's addressed to John Wheeler, the physicist mentioned earlier as a key figure in 20th century physics. From his brother Joe, a soldier serving overseas, Joe knew, in the vague way that many soldiers did at the time, that his brother was involved in something significant back in the United States, some kind of secret scientific project, though he had no idea of the details. What he did know, intimately, was the cost of the war continuing, day after day, in lives. The postcard contained only 2 words: hurry up. Within a few months of sending that message, Joe was killed in action. John Wheeler would later write that he couldn't stop thinking, and never stopped thinking, about how the war might have ended months earlier, potentially saving his brother's life. If certain things had moved faster, that loss shaped the rest of Wheeler's career in a profound way. He turned his formidable intellect toward the most fundamental questions he could find, What is the universe actually made of, at the deepest level, and why does it behave the way it does? Over the following decades, Wheeler became one of the most influential figures in physics, despite never becoming a household name in the way some of his contemporaries did. He trained dozens of graduate students and postdoctoral researchers who would go on to make major contributions across the field, including, as we've already heard, a young David Deutsch. Wheeler's approach to physics has sometimes been described as radical conservatism. Take the laws of physics that are already well established and well tested and push them to their absolute logical extremes, following the reasoning wherever it leads, no matter how strange the destination. In the 1970s, this approach led Wheeler and his students to revisit one of the oldest and strangest experiments in all of quantum mechanics, the double-slit experiment. The basic version of this experiment is famous enough that many people have heard of it. Fire individual particles, photons of light, for instance, at a barrier with two narrow parallel slits cut into it, with a detection screen on the other side. If you don't try to determine which slit each photon passes through, the pattern that builds up on the screen over time is an interference pattern, alternating bands of light and dark, exactly the kind of pattern you'd expect from overlapping waves, like ripples spreading from 2 points dropped into water. But if you set up a detector to determine which slit each photon actually passes through, the interference pattern vanishes. Instead, you get two simple clusters corresponding to particles that went through one slit or the other, behaving like discrete particles rather than spread out waves. Somehow, the act of finding out which path a photon took changes its behavior, even though, in principle, you could imagine the photon as a tiny object, simply goes through one slit or the other, regardless of whether anyone checks. Wheeler pushed this experiment into even stranger territory with a thought experiment that came to be known as the delayed choice experiment. What if, he asked, you let the photon travel most of the way through the apparatus, past the point where if it behaves like a particle, it would have already committed to going through one slit or the other, and only then, at the last possible moment, decided whether to measure which slit it went through, or to let it proceed as if no measurement would happen at all. The astonishing result, later confirmed in real laboratory experiments, is that the photon's earlier behavior, whether it acted like a wave producing interference, or like a particle going through a single slit, depends on a choice made after the photon has, in any classical sense, already passed through the apparatus. If the experiment is set up to measure which slit, the interference pattern disappears, as if the photon had known all along that it would be measured, and had behaved like a particle from the start. Even though that decision was made after the fact, this raises a deeply uncomfortable question. How can a measurement made now affect what a photon did earlier in what seems like the past? Wheeler's answer was, in essence, that the question itself contains a hidden assumption that needs to be discarded. The assumption that the photon did anything definite, took any definite path before the measurement occurred at all. Until the measurement happens, there is no definite history for the photon to have had. The measurement doesn't just reveal a pre-existing fact, it participates in determining what the fact was, retroactively, in a sense. Because there was no fact until that point, Wheeler coined a phrase for the broader philosophy this pointed toward: it from bit. The idea is that the it, meaning any physical object, any particle, any definite physical fact about the universe, ultimately arises from bit, meaning information. Specifically, information obtained through observation or measurement. In Wheeler's view, the universe isn't a collection of pre-existing objects that we passively observe. It's closer to a kind of self-generating loop, where acts of observation and measurement are what give rise to definite physical reality in the first place, with that reality then enabling further observations in an ongoing cycle. This idea was, even by the standards of theoretical physics, extraordinarily radical, and it provoked pushback even from other towering figures in the field. At one lecture, the physicist Paul Dirac reportedly challenged Wheeler directly, asking whether his view implied that the moon doesn't exist in any definite sense, except when someone is looking at it. Wheeler's reported answer was simply yes. Unsurprisingly, it from bit, in its most extreme form, never became a complete working theory of physics in its own right. It was too radical, too difficult to translate into the kind of precise, testable equations that physics demands. But the central insight at its core, that information plays a far more fundamental role in physics than anyone had previously appreciated. That it isn't just a description of physical states, but might be, in some sense, more basic than the physical states themselves, turned out to have real staying power. And, remarkably, within a few decades, that insight would receive concrete experimental backing from a completely unexpected direction: the study of how computers generate heat. In 1961, a physicist named Rolf Landauer was working at IBM, a company that at the time was deeply focused on the practical engineering challenges of building large mainframe computers, machines that filled entire rooms and generated significant amounts of heat during operation. Landauer wasn't trying to uncover deep truths about the nature of reality. He was trying to answer a practical engineering question: is there a fundamental, unavoidable, minimum amount of energy required to process a single piece of information? What he discovered became known as Landauer's principle, and it turned out to have implications reaching far beyond computer engineering. Landauer showed that whenever you erase a single bit of information, whenever you take something that was in one of two possible states, a 1 or a 0, and reset it to a single fixed state, regardless of what it was before, you are reducing the number of possible configurations that bit could be in. Before erasure, the bit could have been either a 1 or a 0. After erasure, it's definitely, say, a 0. With no ambiguity, this reduction in the number of possible configurations corresponds, in the language of thermodynamics, to a reduction in entropy. Entropy being, roughly speaking, a measure of how many different ways a system could be arranged while still looking the same from the outside. But the second law of thermodynamics, one of the most fundamental and exceptionalist laws in all of physics, states that the total entropy of an isolated system can never decrease over time. It can stay the same or increase, but never decrease. So if erasing a bit of information reduces the entropy associated with that bit, something else has to make up the difference. That something else, Landauer showed, is heat. Erasing a bit of information necessarily releases a tiny amount of heat into the surrounding environment, an amount that can be precisely calculated and that depends only on the temperature of the environment, not on the specific technology used to store the information. It doesn't matter whether the bit is stored in a transistor, a mechanical switch, or some exotic future technology. The minimum energy cost of erasing it is fixed by the laws of thermodynamics alone. This was a genuinely profound result, because it meant that information isn't just an abstract mathematical concept, separate from the physical world, something we use to describe physical systems from the outside. Information has a physical cost. Changing it, erasing it, costs energy, in a way that's every bit as real and unavoidable as the energy cost of, say, lifting a weight against gravity. Information, in Landauer's framework, isn't just about the physical world. It is, in a very direct sense, part of the physical world, with its own thermodynamic price tag. And if that's true, then it suggests something striking about every interaction happening throughout the universe, all the time. Every photon absorbed by an atom, every electron moving through a wire, every chemical bond forming or breaking inside a living cell. These aren't just physical events in the traditional sense. They're also, in some sense, computational events. Events that involve information being processed, transformed, sometimes erased, with all the thermodynamic consequences that implies. Decades later, in 2002, a physicist named Anton Zeilinger, who would go on to share the Nobel Prize in Physics, took this line of thinking from theoretical implication to direct experimental demonstration. Working in laboratories in Vienna, Zeilinger and his colleagues conducted experiments on some of the simplest quantum systems available. Things like the spin of a single electron, a property that, in quantum mechanics, can only take on one of two possible values when measured. What Zeilinger's experiments showed was that these elementary quantum systems behave as though they are, fundamentally, containers for exactly one bit of information. No more, no less. This might sound like a fairly mundane technical result, but it connects directly back to one of the longest-standing puzzles in physics. Why does the universe come in discrete chunks at all? Why is energy quantized, existing in fixed packets, rather than being smoothly continuous? Why do certain properties of particles take on only specific, discrete values, rather than any value at all, the way you might naively expect from a smooth, continuous universe? For over a century, since the early days of quantum mechanics, this quantization has simply been treated as a fundamental fact about the universe, something built into the laws of physics, without a deeper explanation for why those laws take that particular form. Zeilinger's work suggests a possible answer. The universe is quantized because information itself is quantized. A single bit, a single yes or no, on or off, 1 or 0, represents the smallest possible unit of definite information that can exist. If physical reality is, at bottom, built from information, then physical reality would naturally inherit that same packet-like structure, not as an arbitrary rule imposed from outside, but as a direct consequence of what information fundamentally is put together. Landauer's discovery that information has a physical, thermodynamic cost, and Zeilinger's demonstration that elementary quantum systems behave as discrete units of information paint a picture that would have made Wheeler's "it from bit" idea seem considerably less like poetry and considerably more like an active, productive line of physics research. If information has real physical weight, real thermodynamic consequences, and if the smallest physical systems we can study behave as the smallest possible units of information, then the idea that the universe, at its most fundamental level, might be made of information, with physical objects and forces being how that information manifests and interacts, stops sounding like a metaphor and starts sounding like a genuine hypothesis about the structure of reality, one with at least some experimental grounding. And if the universe really is, at bottom, information processed according to consistent rules, then there's an immediate and almost unavoidable follow-up question. Information processed according to rules is precisely what a computation is, which means that if the universe is fundamentally information undergoing computation, then the universe is, by definition, the kind of thing that could, in principle, be run on a sufficiently powerful computer, the same way any other computation could be run on a sufficiently powerful computer. And if it's the kind of thing that could be run on a computer, the question of whether someone, somewhere, already has, stops being a question we can simply wave away as obviously absurd. There's one more piece of physics worth bringing into this picture, because it adds a genuinely different angle to the question of computational limits, one that goes beyond anything we've discussed so far, and it comes from thinking carefully about black holes. In the 1970s, physicist Jacob Bekenstein was investigating the thermodynamics of black holes, a topic that, at the time, seemed almost like a mathematical curiosity rather than something with broad implications. Black holes, regions of space where gravity is so strong that nothing, not even light, can escape, have an event horizon, a boundary beyond which nothing inside can ever communicate with the outside universe again. Bekenstein, along with Stephen Hawking, showed that black holes have an entropy, a measure of the information associated with them, and that this entropy is proportional not to the volume of the black hole, as you might naively expect for any three-dimensional object, but to the surface area of its event horizon. This led to what's now called the Bekenstein bound, a fundamental limit on how much information can be contained within any region of space, a limit that depends on the area of the boundary surrounding that region, not its volume. This result generalizes into something called the holographic principle, the idea that the maximum amount of information that can be packed into any volume of space is fundamentally limited by the area of its boundary, measured in fundamental units related to the Planck scale we discussed earlier. In a sense, this suggests that a three-dimensional region of space might be fully describable by information encoded on its two-dimensional boundary, the way a hologram encodes a three-dimensional image on a flat surface. Why does this matter for the simulation question? Because it provides an independent, completely different route to the same kind of conclusion we reached earlier from the Egan and Lineweaver calculation. The universe has a finite information content, a finite number of bits required to describe it, and that number, while staggeringly large, is not infinite. The holographic principle arrives at this conclusion not by counting particles and their possible states directly, but by thinking about the geometry of space itself and the relationship between information and the boundaries of regions. The fact that two very different approaches, one based on counting particle states, the other based on the thermodynamics of black holes and the geometry of space-time. Both point toward the universe having a finite, calculable information content. Is a striking convergence. There's a related concept worth mentioning too, named after the physicist Hans Bremermann, who in the 1960s proposed a limit on the maximum rate at which any physical system can process information, based on fundamental constants like the speed of light and Planck's constant. Bremermann's limit suggests that there's a maximum number of bits per second per kilogram of mass that any computational system, anywhere built from any conceivable technology, could ever process, a limit set not by engineering constraints but by the basic structure of physics itself. Put these together, a finite total information content for the universe, a finite maximum rate at which any system can process information, and a finite minimum energy cost for changing information, established by Landauer, and what emerges is a strikingly consistent picture. Whatever the universe is, whether it's a simulation or not, it behaves, at every level we can currently probe, as a finite, bounded computational system, with hard limits on storage, processing speed, and the energy cost of operations. These aren't properties we'd expect from an infinite, continuous, unbounded reality with no underlying computational structure at all. They're exactly the kinds of properties you'd expect from a system, however vast, that ultimately runs on something with finite resources. Of course, finite is a relative term here. The numbers involved, 10 to the power of 122 bits for the information content of the observable universe, are so far beyond anything humanity could ever hope to build or even meaningfully compare to our own technology that, for all practical purposes, they might as well be infinite from our perspective. But finite, even if astronomically large, and literally infinite and unbounded, are very different claims, philosophically and physically, and the evidence, as best we can currently tell, points toward the former. This finite, bounded character of the universe doesn't, on its own, tell us whether we're in a simulation. A genuinely fundamental, non-simulated universe could perfectly well have finite information content and finite processing limits as basic features of its own nature, without any of that implying it was built or run by anything. But it does mean that the universe is, at minimum, the kind of thing that could be simulated, in principle, by a system with sufficiently vast, but still finite, resources. It rules out the easiest objection, the idea that the universe is simply too infinite, too unbounded, for the question to even make sense. The question makes sense. The numbers are just almost incomprehensibly large. So, with all of this assembled, the staggering information content of the universe, the finite limits suggested by the holographic principle and Bremermann's bound, the optimization-like behavior of quantum mechanics, the thermodynamic reality of information established by and its experimental quantization demonstrated by we're now in a position to return to where we started, Bostrom's argument, and the question of what, if anything, all of this actually tells us about whether we're living inside a simulation. So here's where things stand. Everything we've covered, the optimization-like features of physics, the thermodynamic reality of information, the quantization of elementary systems, the finite information content suggested by multiple independent lines of reasoning, is at least consistent with the idea that our universe could be the kind of thing that gets simulated. None of it proves that it is being simulated, but crucially, none of it rules the possibility out either. If anything, the deeper physics digs, the less obviously absurd the question becomes. But consistent with and true are very different things. And this is where we have to be honest about the limits of what we actually know. Because there's a counter-argument to Bostrom's reasoning that's just as important as the argument itself. And it comes from a place of genuine humility about our evidence. Bostrom's entire argument rests on a single load-bearing assumption that it's possible, at least in principle, for a civilization to build a computer capable of simulating conscious minds in enough detail that those minds would be indistinguishable from the inside from biological minds. Everything else, the statistical overwhelming of biological minds by simulated ones, the trilemma, the ancestor simulation hypothesis, the nested simulation stack, all of it depends on that one assumption being true. And here's the thing, we don't actually know that it's true. We've never done it. As advanced as our current artificial intelligence systems are, and they are genuinely remarkable, nobody has built, or has any concrete idea how to build, a system that's widely agreed to be conscious in the way a human being is conscious. We don't have a single confirmed example of a simulated mind anywhere by anyone, including ourselves, and we haven't encountered any evidence of other civilizations either, advanced or otherwise, who have done it. This connects to a much older puzzle in astronomy and astrobiology, sometimes called the Fermi paradox, named after physicist Enrico Fermi, who reportedly posed a simple but startling question during a casual conversation in the 1950s. Given the sheer number of stars and potentially habitable planets in our galaxy, and given the amount of time the galaxy has existed, where is everybody? If advanced civilizations are common, and if at least some of them eventually develop the kind of technology Bostrom's argument requires, we might expect to see some evidence of that somewhere by now. We don't now. The absence of evidence for advanced alien civilizations doesn't tell us much on its own. The galaxy is enormous, and our ability to detect distant civilizations is limited in ways that are well understood and not particularly mysterious. But it does mean that, when it comes to the specific question Bostrom's argument hinges on, whether minds can be simulated in sufficient detail to be indistinguishable from biological ones, our evidence is essentially limited to a sample size of exactly 0 confirmed cases, drawn from a single civilization, our own, that hasn't yet developed the relevant technology. Trying to estimate a probability from a sample size of 0 is, to put it mildly, statistically fraught. And yet, some researchers have tried to do exactly that, in a rigorous way, simply to see what comes out the other end. One notable attempt comes from astronomer David Kipping, who approached the question using Bayesian reasoning, a statistical framework for updating probability estimates as new information becomes available, starting from some initial assumption and revising it based on evidence. Kipping set up the problem by considering the different possibilities Bostrom outlined, essentially that simulating conscious minds is possible and gets done, or that it's possible but doesn't get done, or that it's simply not possible at all, and asked what the available evidence, which is to say, the fact that we exist, were having this conversation. and we haven't yet built or encountered such a simulation ourselves, implies about the relative likelihood of these scenarios. The result of Kipping's calculation came out close to even odds, somewhere in the neighborhood of 50%. Not because the universe is fundamentally undecided about the matter. Of course, the truth, whatever it is presumably fixed. But because the mathematical framework, given essentially no strong evidence pointing in either direction, naturally lands close to a coin flip. It's the statistical equivalent of saying, based on what we currently know, we genuinely cannot tell. And any confident claim in either direction is going beyond what the evidence supports. This might feel like an anticlimactic conclusion after everything we've covered, the staggering scale of the data we'd need, the physics that hints at computational underpinnings, the philosophical arguments stretching back centuries, the experimental work demonstrating the physical reality of information itself. And in a sense, it is anticlimactic, but it's also, in its own way, the most honest possible answer, and arguably more interesting than a confident yes or no would be, because it tells us something important about the current state of human knowledge. We've pushed our understanding of physics, computation, and consciousness far enough to take this question seriously, to identify what evidence would actually be relevant to it, and to see how it connects to some of the deepest open problems in science, but not far enough to actually answer it. And that, in itself, is worth sitting with for a moment. A question that, a few centuries ago, would have belonged entirely to theology or pure speculative philosophy, with no obvious connection to anything testable, now sits at a genuine intersection of cosmology, quantum physics, computer science, and the philosophy of mind, each of which has something concrete and substantive to contribute to it. That's a remarkable amount of intellectual progress, even if the final answer remains out of reach for now. So where does this leave Bostrom's original trilemma, and the worry that started this entire line of inquiry? The idea that figuring out whether we're in a simulation might tell us something about whether humanity is likely to survive long enough to build one ourselves. The honest answer is, it leaves it exactly where it was. We don't know whether we're in a simulation, which means we don't get either piece of information Bostrom's argument would have given us. No reassurance that we're not doomed, but also no confirmation that we are. What we do have, though, is a much clearer picture of what it would actually take to answer this question. What kind of evidence would matter? And what major scientific milestones in computing, in physics, in our understanding of consciousness would need to be reached before the question moves from currently unanswerable to potentially answerable? And several of those milestones are things that active research is working toward right now, for entirely independent reasons that have nothing to do with simulation theory at all. Consider quantum computing first. We mentioned earlier that the most powerful publicly known quantum computer currently contains a little over 1,000 qubits. That number has been climbing steadily, roughly doubling every few years, in a pattern that researchers in the field sometimes compare to the historical growth of classical computing power, though the comparison is imperfect because qubits face challenges, particularly around error rates and maintaining stable quantum states that don't have direct analogs in classical computing. If quantum computers continue to scale, And if researchers continue to make progress on quantum error correction, the technique of using many physical qubits to represent a smaller number of more reliable logical qubits, then at some point in the coming decades, it may become possible to simulate genuinely complex quantum systems, not just small molecules or simple particle interactions, but systems approaching the complexity of, say, the chemistry happening inside a living cell, or the quantum effects involved in photosynthesis or high-temperature superconductivity, phenomena that remain poorly understood, partly because classical computers simply can't model them in enough detail. None of this would, on its own, tell us whether we're in a simulation, but it would represent meaningful progress on one of the prerequisites. Bostrom's argument depends on a civilization's ability to simulate increasingly complex quantum systems. If humanity reaches a point where we can routinely simulate quantum chemistry at the scale of, say, a single neuron, that would be a genuinely significant milestone, both for medicine and materials science, which are the actual reasons this research is funded, and, almost as a side effect, for understanding where the limits of computation actually lie. Then there's the observational side, the kind of work being done by instruments like the Vera Rubin Observatory we discussed earlier. Over its planned survey, that observatory and others like it will dramatically expand our catalog of the universe. More stars, more galaxies, more transient events like supernova and gravitational wave sources. While none of this data will directly address simulation theory, it does something arguably more important for this conversation. It continues to test our fundamental physical theories against reality, at larger scales and with greater precision than ever before. If our universe really does have some kind of underlying computational structure, the kind of thing that might produce subtle, unexpected patterns, perhaps tiny inconsistencies in physical constants across vast distances, or unexpected statistical patterns in the cosmic microwave background, the faint afterglow of the early universe that permeates all of space, then surveys like this are exactly the kind of project that could, in principle, eventually notice such things, simply by virtue of gathering enormous amounts of high-precision data and looking for anything that doesn't fit existing models. It's worth being careful here, though, because this is exactly the kind of reasoning that can tip over into seeing patterns that aren't really there. Throughout the history of physics, there have been moments where unexplained anomalies in data turned out to be genuine new physics, and many, many more moments where they turned out to be measurement errors, statistical flukes, or gaps in existing theory that got resolved without requiring anything exotic. If a glitch in the simulation-type anomaly were ever found in cosmological data, the overwhelmingly more likely explanation, based on the history of science, would be that it represents new, real physics we don't yet understand, not literal evidence of an external simulation, but new physics we don't yet understand is, in its own way, exactly the kind of thing this entire conversation has been circling around from the start. There's also ongoing work in fundamental physics, aimed at finding a theory of quantum gravity, a framework that successfully combines general relativity, our theory of gravity and large-scale structure, with quantum mechanics, our theory of the very small. These two theories are both extraordinarily successful within their own domains. but they're famously incompatible with each other in certain extreme situations, like the center of a black hole or the first fraction of a second after the Big Bang. Finding a theory that unifies them has been one of the central goals of theoretical physics for nearly a century. Several candidate approaches exist, including string theory and the loop quantum gravity framework mentioned earlier, each making different predictions about the fundamental structure of spacetime at the smallest scales. If one of these frameworks, or some future framework not yet developed, turns out to be correct, and if it confirms that spacetime really is discrete at the Planck scale, made up of indivisible units rather than being perfectly smooth and continuous, that would be one of the most significant confirmations yet of the idea that the universe has a finite, granular structure, the kind of structure that would be a prerequisite for any computational description of reality, simulated or not. And then there's the hardest problem of all. In some ways, harder than anything in physics, understanding consciousness itself. This remains one of the genuinely unsolved problems in science, sometimes called the hard problem of consciousness. The question of why and how physical processes, neurons firing, electrical signals, chemical reactions, give rise to subjective experience at all. Why does processing information in a certain way feel like something from the inside rather than just happening, the way it presumably happens inside a calculator or a thermostat with no one home, so to speak? This question matters enormously for everything we've discussed, because Bostrom's entire argument depends on the idea that consciousness could, in principle, arise from sufficiently sophisticated information processing, regardless of the substrate, whether that's biological neurons or some artificial system. If it turns out that consciousness specifically requires biological processes, something about the particular chemistry of neurons that can't be replicated in silicon or any other substrate, no matter how sophisticated, then the entire foundation of the simulation argument changes. Simulated minds, in the sense Bostrom means, might simply not be possible, regardless of how powerful computers become. Conversely, if researchers eventually develop a robust, testable theory of consciousness, one that can predict in advance whether a given system, biological or artificial, is conscious or not, based on its structure and information processing patterns, rather than just its behavior, that would be one of the most significant scientific achievements in history, with implications reaching into medicine, artificial intelligence, animal welfare, and yes, eventually, the simulation question too. Several research programs are actively working on theories along these lines, attempting to identify the specific structural or informational properties that might be necessary and sufficient for conscious experience, though none has yet achieved the kind of broad consensus and experimental confirmation that would settle the matter. So, when people ask what's actually being done to figure out whether we live in a simulation, the honest answer is nothing directly, because there's currently no experiment anyone could design that would test that question specifically. But almost everything happening at the frontiers of physics, cosmology, computing, and neuroscience right now is, in one way or another, chipping away at the prerequisites and assumptions that the question depends on. Each of these fields is making genuine progress for its own reasons, on problems that happen to also be the exact problems standing between us and an answer to Bostrom's question. So let's bring this all together. We started with a philosopher who spends his nights cataloging the ways humanity might end, and a probability argument that seemed to suggest we're either almost certainly simulated, or living in a civilization unlikely to survive long enough to become the kind of civilization that simulates others. We then asked what it would actually take to simulate a universe like ours, and found numbers so large, 10 to the power of 122 bits for the observable universe alone, that they break our usual intuitions entirely. We looked at how real simulations work, from galaxy formation models that skip detail in empty space, to weather forecasts that can't track individual raindrops, to nuclear weapons simulations running on repurposed gaming hardware, and found a consistent pattern. Every simulation approximates, allocating detail only where it matters for the question being asked. We then asked whether the universe itself shows signs of this kind of approximation, and found several intriguing, if inconclusive, candidates. The speed of light behaving like an information propagation limit, the fine-tuning of physical constants looking like parameter selection, the Planck scale suggesting a minimum resolution, and quantum mechanics behaving as though reality is only rendered upon observation. We explored why quantum mechanics, in particular, represents the single largest obstacle to any complete simulation, requiring an entirely different kind of computer, a quantum computer, built on principles that didn't even exist as engineering concepts until the 1980s, and which remain, even today, in relatively early stages of development. We looked at the problem of emergence, the fact that even perfect knowledge of fundamental physics doesn't automatically tell you how proteins fold, how brains think, or how galaxies form, and recognized that any simulation detailed enough to matter would need to solve this problem too, producing not just particles obeying rules, but the vast, layered complexity of chemistry, biology, and minds. We then turned to consciousness directly, looking at how modern artificial intelligence, despite its remarkable fluency, remains a subject of genuine debate when it comes to whether it understands anything at all, let alone experiences anything. We considered what it would mean for free will if minds could be simulated, and found that the presence of genuine quantum randomness might mean that even a simulated existence wouldn't have to be a scripted one. From there, we went even further back to philosophical traditions stretching across continents and centuries, all circling the same fundamental problem. How do you verify from the inside that your experience corresponds to anything real at all? Descartes' demon, Putnam's brain in a vat, and Hoffman's evolutionary argument that perception is built for usefulness rather than accuracy, all point toward the same unsettling conclusion. There may be no internal test that could ever distinguish a sufficiently good simulation from reality, which means the Matrix's central premise that you could wake up into the real world doesn't actually hold up, because waking up into another simulation would feel identical. This led directly to Bostrom's sharper claim that if simulations of conscious minds are possible at all, the most likely kind to be run overwhelmingly would be simulations of a civilization's own ancestors, run repeatedly by descendants curious about their own origins, potentially nested many layers deep with the original biological reality, if it exists at all in any accessible sense, buried under a number of layers we'd have no way of counting. We then turned to the physics of information itself. John Wheeler's deeply personal motivation for pursuing the deepest questions in physics, his radical it from bit philosophy, and the experimental work decades later by Landauer and Zeilinger that gave that philosophy real teeth. Information has a physical cost, and elementary quantum systems behave as the smallest possible units of information, suggesting that the universe's quantized structure might be a direct consequence of information's own quantized nature. Finding that multiple independent lines of physics converge on the idea that the universe, however vast, has a finite information content and finite processing limits, the kind of properties you'd expect from something that could, in principle, be computed. And finally, we came back to the question of evidence and found that despite everything, the honest answer remains: we don't know. And the best rigorous attempts to estimate an answer land close to 50, not because the truth is genuinely balanced, but because our evidence is essentially non-existent, drawn from a sample size of 0 confirmed simulated minds anywhere, including our own civilization. What's genuinely remarkable, though, is how much real, substantive science this question connects to. It's not a question that exists in isolation, disconnected from everything else we study. It sits at a crossroads, touching cosmology and the large-scale structure of the universe, quantum mechanics and the behavior of the smallest particles, computer science and the theoretical limits of computation, thermodynamics and the physical cost of information, and philosophy of mind and the nature of consciousness itself. Progress in any of these fields, progress that's happening right now, for reasons that have nothing to do with simulation theory, chips away at the open questions this entire line of reasoning depends on. There's also something worth noting about why this question, despite being currently unanswerable, isn't a waste of time to think about. Thought experiments that seem, at first, like idle speculation have a long history of turning out to be productive in ways nobody anticipated. Einstein's thought experiments about riding alongside a beam of light led, eventually, to special relativity. Schrödinger's famous cat, originally intended as a kind of reductio ad absurdum, a way of highlighting what he saw as an absurd implication of quantum mechanics, became one of the most productive ways of thinking about superposition and measurement, still actively used in quantum computing research today. The simulation argument, whatever its ultimate answer, has already proven useful as a framework for thinking clearly about information, computation, and the relationship between physical law and physical reality in ways that connect genuinely disparate fields of research. So where does that leave us, practically speaking? Probably exactly where it left us at the start, going about our days, experiencing whatever this is, whether it's base reality, a simulation of a simulation, or something else entirely that none of our current frameworks have even imagined yet. The honest, grounded answer is that we don't know. We currently have no way to know. And the path toward potentially knowing runs through some of the hardest open problems in all of science. Problems that may take decades or centuries, or may never be fully resolved at all. But there's something almost reassuring in that uncertainty, too. if a sufficiently advanced simulation really is indistinguishable from reality in every way that matters, experientially, emotionally, scientifically, then the practical difference between living in one and not living in one may be, for all intents and purposes, zero. The sunsets still look the way they look. The people you care about still matter, in every sense that's ever mattered to anyone. The curiosity that led you to wonder about any of this in the first place is, itself, real. In whatever sense anything is ever real. A genuine act of a genuine mind, wherever and however that mind happens to be running. If you found this exploration of where physics, computation, and philosophy collide interesting, there's a lot more territory like this worth exploring. The kind of questions that sit right at the edge of what we currently understand, where the answers aren't settled yet, but where the questions themselves are sharp enough to actually mean something. Following along for more of these deep dives, and leaving a comment with your own take on which part of this argument you find most or least convincing, genuinely helps keep this kind of content going, and often shapes which topics get covered next. For now, the universe, simulated or not, continues doing whatever it's doing, quietly processing, computing, or simply existing, depending on which framework turns out to be correct, while we continue asking questions about it, which is, in the end, perhaps the most human thing of all, regardless of what kind of hardware happens to be running the process.